Welcome to the next in our Masterclass series. This time we're going to be discussing geometallurgical modelling. Just to remind you, the Masterclass series is about comminution, so I'll be talking purely about the comminution modelling side of geometallurgical modelling. Geometallurgical modelling, of course, is a much broader discipline than simply comminution. There are two broad approaches to comminution modelling in geomet models. They both, as we'll see, effectively reduce down to the same thing. We need for our model all characteristics, and that information is provided from a block model, and we can see here on the left a pit outline, and that's been divided up into blocks. Each of these blocks will have all characterization information, and that information needs then to be combined in some way and then fed to our geomet model equations, and those equations are designed, should be designed, to provide a forecast, and typically the forecast we are looking for is the throughput of the comminution circuit. In this approach, there's an additional interim step, simulation, where all characteristics are passed from the block model through to a simulation model of the comminution circuit, and that simulation model generates data which in turn are fed to the geomet model, which in turn produces our forecast. We discussed all comminution characteristics in a previous masterclass, so I'm not going to go through all the different laboratory tests and all the different all comminution characteristics that one could use in the block model. Needless to say, you need to make sure that whatever characteristics you use, they are appropriate in the sense that they reflect the comminution equipment response that you're looking to predict or forecast. So, for example, there's really no point in having a crushing work index, for example, if you are looking to forecast the performance of a ball mill circuit. There's also a temptation, and I really do understand the temptation, to rather than go for laboratory tests, the appropriate laboratory tests that give you whatever the comminution characteristics you're looking for, people try and look for a proxy test, cheaper test. And the problem with these is that quite often they don't correlate with all ore types in the same way in your deposit. So you may well find initially a very good proxy for ore type A. As you develop your pit and a new ore type B for example, comes along, that proxy test does not correlate in the same way. And if you don't know that, and we're going to look at an example later on, then your forecast can prove quite disastrously wrong. There's also certainly cases where people have looked for, rather than proxy tests, to see whether they can correlate comminution performance with information such as chemical assays, mineral content, structure, and so on. That information is often available in quite a great amount of detail, because it's data that the geologist would collect on the ore body. My experience has been it is very rare indeed that you can get any reasonable correlation that's going to give you anything other than very crude estimates of comminution characteristics. So try and avoid that as well. We've also talked before in a previous masterclass about numbers of tests so that you can have sufficient resolution required for your forecast. So that's also something that you need to be mindful of. And last but not least, whatever comminution parameters you have in your block model, they have to have the units that are able to be Kriged or blended. And the reason I mention that is that some parameters cannot be Kriged or blended, and you need to be aware of that. What's Kriging, for those of you who may not have heard the term, or have heard the term but perhaps don't understand what it is? Kriging was developed by a guy called Kriged, a South African man. The early 1950s, I think it was 1951. It came from his master's thesis. It's a geostatistical method for spatial interpolation of information as applied to our pit. And in our case, we're looking at hardness information. It could be used, if we look at this false color map on the left hand side as an example, to interpolate between these crosses, these black crosses. Let's say these black crosses represent the results from laboratory tests on drill cores, and this is a slice, a horizontal slice through our pit. And what Kriging enables us to do is to interpolate between these different points where we have hard data to areas in the pit where we have less information, and it gives us the best estimate of what the hardnesses are between those various points. So again, looking at this left hand side, let's say red represents the very hardest ore and blue the very softest. So Kriging enables us to make these contour maps, and from these contour maps we can now, in some blocks, let's look at this block here for example, we've got no black crosses, which means we have no direct data in that block. We can interpolate with the best confidence that we're able to, given the data, and say, well, the hardness is likely to be of whatever that light blue represents mathematically. And on the right hand side is just another example of a false color map that could be generated through Kriging techniques. So what sort of parameters can and can't be Kriged or blended? So let's look at some. Let's assume our blocks are represented in tons, which is actually not quite correct. They're usually represented in volume. If it's constant specific gravity, then all the volumes of course are the same tons. But for the purposes of this exercise and illustrating the point I'm trying to make, let's say we're looking at equal tonnages for all our blocks. Then, for example, kilowatt hours per ton can be Kriged or blended, and any hardness parameter which has the units of kilowatt hours per ton is fine. There are no problems. And if we compare that to, for example, metal grade, which is in grams per ton, for example, grams per ton of copper, they can be Kriged and blended. So if you're ever in any doubt, just think of kilowatt hours per ton. You compare that to grade, grams of copper per ton. Kilowatt hours per ton you can think of as being an energy grade. It's the number of kilowatt hours needed to be expended to process that ton. So those units are fine. Many of you will be familiar with the JK, A and B parameters. They cannot be Kriged or blended independently. A times B is a common parameter used to infer hardness. Its units are tons per kilowatt hour. So because tons are not in the denominator, it can't be Kriged directly. What you can do is invert A times B, and you can then Kriged or blend inverted A times B. Another good example of a parameter that can't be Kriged is tons per hour. So just to reiterate, basically any parameter that does not have the units of per ton cannot be Kriged. The reason I'm making a point about this is that I've seen some really quite serious mistakes made if that rule is not adhered to. So why can't some hardness parameters be Kriged or blended? And I want to use as an example this very simple situation concerning speed and a journey which is taken in two parts. The first part of the journey, I travel 100 kilometers at a fixed speed of 150 kilometers an hour. The second part of my journey is also 100 kilometers, but now I reduce my speed to 50 kilometers per hour. And what I want to do is to calculate the average speed over the entire journey. So, average speed, 150 plus 50 divided by 2, 100 kilometers an hour. It looks like it should be the right answer, but unfortunately, it's not. Totally wrong. The correct way to do the calculation is not to average the speeds. It is to determine the total distance divided by the total time. Now the total time, if we look at the first part of the journey, 100 kilometers, 150 kilometers an hour, the time for that part of the journey is 100 divided by 150. For the second part of the journey, the time is 100 divided by 50, and so therefore the average speed is given by this term here. Total distance, 200 divided by the total time. And the correct answer is 75 kilometers an hour, not 100. And that is, of course, a very, very big difference. And if you think about hardness, and let's say these numbers related to hardness, we'd be looking at 25% difference between our correct value and incorrect value. And the consequences of that, when we're looking at forecasting, as I think you can understand, are significant. So, reiterating, from Kriging viewpoint, you have to have units of per ton if you're to get the right answer. So before we look at some specific examples of comminution models for geomet modeling, let's just look at the general approach that might be adopted from beginning to, I'm not going to say end, because one of the things I want to emphasize with you is that geomet modeling is not a one-off thing. You should be developing a geomet model for long-term forecasting. And it doesn't mean you just generate it at the beginning and then that's it forever. It is something you have to keep going back to, keep improving on if you're to do it successfully. So we start initially, of course, we need to populate our block model with appropriate hardness data. We then need to, from that block model, obtain hardness data from block to block to block. And we can also look at obtaining other relevant information that might be stored in the block model. And I'm going to talk a little bit about what that other relevant information might be. And it varies from mine site to mine site to other information that could or could not be useful for developing your comminution modeling. Depending on the mine plan, then you'll need to probably blend characteristics from different blocks, because quite often material comes from different blocks in the pit as it's delivered to the comminution circuit. So you now have blended characteristics, and once you've got that information, you need to develop an equation that takes that information to predict kilowatt hours per ton. You then use that equation together with the mill power draw, and I'm specifically here looking at milling circuits, and from the mill power draw divided by your predicted kilowatt hours per ton, you can obtain a forecast tons per hour, forecast throughput. Before you let that model loose and you start forecasting and acting on your forecast, the first thing you do is to compare those predictions historically. So look at historic production data and see how well your model works. Almost certainly you will need to incorporate some empirical corrections where necessary. You are never, I'll be very surprised if from first principles you can come up with an equation that predicts kilowatt hours per tonne of your circuit without any fitting to historic data. So you've now reached the point where you've got an equation, you've incorporated some historical empirical corrections, you now let your equation loose and you forecast the future throughput. When that future comes, let's say you forecast next month's throughput, you now need to reconcile. When that month is over, collect your data and compare what you predicted to what actually happens. Once you've done that, if you have a good prediction, then there's nothing needed to be done. But you need to continue to monitor that month after month after month. And in many cases you will find situations will arise where maybe your prediction starts to drift away from what actually happens in practice. And we're going to look at that in a minute, where it happened at one particular plant. What you then need to be looking at doing is possibly looping back to earlier parts of your development program. It might mean you have insufficient ore characterization data and therefore you need to do more test work. It may mean that there are some problems on your plant that you're not aware of that are limiting throughput. It's not a hardness problem, it is some other bottleneck problem that's causing that. What I'm trying to say is you have to continuously reconcile, forecast, modify so that at all times your model is the very best that you can make to ensure that your forecast is of the highest quality. So let's have a look at an example of a power-based model approach, and this is based on some work that I did at a mine site quite a few years ago now, so it is a real example. This equation here I published, I think, back in 2004, and it's a design equation, and its purpose is to predict the autogenous, semi-autogenous mill specific energy, and it is a function of the feed size, ore hardness, ball load in the mill, speed of the mill, and the design, the aspect ratio of the mill. All these terms here influence the specific energy. Now, this particular circuit I was working with, the speed was fixed, the ball load just about was fixed, it was kept as best they could at round about 15%, and the aspect ratio, of course, I knew from the measurements of the mill. So the previous design equation, three of those terms basically could be knocked out and reduced to this equation here, which basically says that the specific energy of the SAG mill is simply a function of the feed size, in this case the F80, and the hardness. And I had drop weight index information from the block model because they had done SMC tests to develop the ore characterization profile of their pit. So now we have a term in which the block model can provide this, and all we're really now looking for is some term that will give us a relationship that will indicate the F80. And depending on what other information is available, and if you remember in the previous slide I mentioned about looking for other information that might help. In a lot of cases that information could be powder factor, blast design, RQD, which is to do with structure, UCS or point load indices. I put the DWiª here because in fact the DWiª is correlated, we find, with the F80. So DWiª itself could be used as an indicator of the F80, and primary crusher closed side setting. Now, why have I indicated powder factor and blast design? And that's simply because we know that the run of mine size distribution, which itself is a function of how the miners blast that ore, and is a function of the structure, and RQD gives you that information. A highly structured ore, an ore with a lot of fractures and cracks and joints, tends to give you a finer run of mine, and a finer run of mine typically gives you a finer SAG mill feed. So there's an opportunity, if you have some of this information, extra information, to use that to develop some equation which helps indicate what the F80 is, over and above the influence of hardness on that. So I've got a basic equation, at least to begin with. How do I see whether it works? How do I calibrate it? Well, you start with real plant data. You have plenty of it. This part of the geometallurgical modelling, for me, I have to confess, is the most enjoyable. If you are working on a well-run plant, which is well instrumented, and you can get access to historic data like I was able to here, then it gives you that opportunity of developing something which is really quite special. And me particularly, I like looking at patterns in data and trying to work out why those patterns exist. And if you can work that out, then you have a geometallurgical model. My advice is, when you're trying to develop a geometallurgical model, make the assumption that simple is best. Quite often it is. If it's not, then make your model more complicated and sophisticated as you go on and develop it further. So in this particular case, I decided to start with the very simplest model I could possibly devise. And if you remember that previous equation, it said kilowatt hours per tonne as a function of F80 and DWiª. Well, I decided to go one step simpler and say that specific energy is simply a function of just the DWiª, the hardness, and a constant K. So throughput, therefore, the throughput forecast was based on the mill power draw divided by the mill specific energy, and the mill specific energy was estimated through multiplying the DWiª by some empirical function. And that empirical function had to be found by trying to fit that equation to these blue data points, which are real throughputs, real historic throughputs from this particular comminution circuit. And the mine planning department generated all these blue data points for me, and for each of those periods that they covered, they interrogated the block model. They looked at, from the mine plan, what tonnages from each of those blocks at each of those data points was treated by the plant, and they provided me with a weighted DWiª from their block model for each of these data points. Now, one of the things I should point out to you that you need to be aware of is that this exercise, of course, is trying to match, in this case, these blue real data points with predicted data points, and these are these purple ones. When ore is blasted in the pit, it actually takes time before that ore reaches the plant. And that lag can be actually quite significant, and you need to be aware of it, because what we're trying to do is match up here is what the mine plan says happened in the pit with respect to ore. And if there is an ore change, for example, today in our mine, we might not see that ore change coming through to our grinding circuit for 1 day, 2 days, even longer. So the mine plan would say to me, for one of these blue data points, there has been a change in ore at this particular day, but the process plant won't see that change for several days later. And so if you don't recognize that lag, you sometimes find it very difficult to match up the peaks and the troughs because of that time lag. But once you've recognized what that time lag is, and it's fairly easy to calculate it, in that you look for where there has most certainly been a change in the mine plan, and most of us on plants know certain parts of the pit has an ore which does X and certain parts of the pit has an ore which does Y. We've seen it going through our comminution circuit. So you look for a time when the mine plan has had a big shift from one of those ore types to the other. We know when that shift is made in the mine, and then we just simply look how many days or how many hours even later does our mill now start to respond. And that is some indication of the lag between what happens in the mine, and specifically when there is an ore change, to when that response comes through to the plant. So I did that with this data, and I can't remember what the lag was, but I incorporated it in me matching things up. And so what this these purple points are now is me fitting the best K value that I could, so that I got the best correspondence between the actual and the predicted. Now, what we can see is that for most of the time, it's actually not bad, considering it is such a very, very simple model. Interestingly though, here we can see it really could have been better, and there's a couple of other places where we look and think, well, I possibly could improve that further. So what I did is look at whether I could see from this period here anything that was unusual from a range of other information that I had available which described the ore. And one of those bits of information was the RQD. As I said before, RQD is an indication of the structure of the rock, and what was very noticeable was for this period here there was a distinct change in the RQD. So I reconfigured my equation to now have an RQD term in, and then refitted, and this is what we ended up with. And there is an improvement. It's not as good as I would have liked, but there certainly is an improvement to the fit of the data in that period, and there was also a corresponding improvement in certain places to the data at other terms. So I felt that yes, RQD was beneficial. So next I decided to see whether powder factor was able to help improve the fit, and in this particular case powder factor did. I was very pleased with the improvement that powder factor made to the fit of the observed and predicted throughput. And at this particular point, I stopped the development of the model any further. I did try a couple of other ideas, but I really couldn't get a better fit than that. The point I'm trying to illustrate here is, and the process is, start simple, look to see where your simple model doesn't work, try and find out why, try and see whether where it doesn't work there are other data available that might indicate why, and incorporate additional terms. Don't make the mistake maybe of just putting in as much data as you can possibly find and then hitting the data with some multiple linear regression equation and hope for the best. You might end up with something which is quite good, but my advice is you really do need to work with your data, understand your data, understand the response of your circuit and what are the drivers. And as I said earlier, if you understand it, then you've got a model. If you're interested in reading up and published papers of mines that have gone the route of power-based approaches to throughput forecast models, I would thoroughly recommend Batu Hijau's papers, and we're actually going to look in the next 5 to 10 minutes of the approach that they took. There are a number of papers. I've just put two here. Perhaps the most relevant is this second one here that was given at the SAG conference in 2011. There's also another very, very good one that was published in 2013 at Prosamin, and it's to do with the model that these four guys looked at for Los Prolambris. So let's look at Batu Hijau, and all the data I'm going to present is taken from that SAG conference paper. I actually did do a lot of work with Batu Hijau over the years, but the data I'm going to present here is straight out of that paper. Batu Hijau had a long history of developing geometallurgical models. They did a really, really thorough job over many years. They went the mine to mill route and made great use of the mine to mill strategies to optimize their mine and their circuit. One of their early initial models, circuit throughput models, incorporated terms such as powder factor, RQD, and they used the point load index as a SAG mill hardness proxy. Now, if you remember, I said before, powder factor influences ROM, and of course ROM influences the SAG F80, and also RQD does as well. So just like I said in that previous example, they started with something really quite robust, really good, relatively simple, with terms that they had readily available from the mine plan and from their block model. This is what that initial model looked like for the first year of its application. It was during the period 2007, and there are periods where it works quite well, but there are a couple of periods where things started to go a little bit off track. Here in particular, we started to notice that the model was predicting higher throughputs than the plant was actually getting, and it was noted that corresponded to a change to lower grade ore. The point load index said that the lower grade ore basically had the same hardness as higher grade ore, but when we did some test work, we found, we did some SMC test work, we found that in fact the lower grade ore was harder, and for some reason the point load index didn't correlate with that lower grade ore hardness. And if you remember what I said, one of the very earliest slides in this presentation, one must be very, very careful about the use of proxies. The other thing that was noted was round about this period here, whereas previously the circuit most of the time was SAG mill limited, we started to see periods where it was the ball mill circuit that was limiting throughput rather than the SAG mill circuit. And of course our equation, if you remember our very simple equation, was really all based on SAG mill performance, no recognition of what the ball mill circuit influence might be. And that was simply because at that time there was no indication whatsoever that the ball mill circuit in any way limited the throughput of the comminution circuit. So what was done to improve the situation, to improve the forecast capability of the model? Well, the plant team, at the time I think it was being led by Karen McCaffrey, did two things. They repopulated the block model with DWiª data. They did a lot of SMC tests, and that DWiª data replaced the point load index. And the second modification they did was to recognize the fact that in some cases the throughput of the circuit was ball mill limited. So they ended up with a two-part model. This first part of the model was invoked when the ball mill work index was less than, in this case, 12.25 kilowatt hours per tonne. And under those circumstances, the circuit was not ball mill limited, it was sag mill limited, and this equation was used. However, once the ball mill work index reached 12.25 and exceeded it, then this alternative equation was used, and this represents the circuit throughput capabilities when it is ball mill limited. Did it work? Well, just to go back to the original graph, the original model that I showed you, so you can just remember the extent to which that early model did or didn't fit the data. And this is what the revised model looked like. So much better agreement and correspondence throughout that entire period. Those previous plots give us a good indication of how good the models are really by eye, but at the end of the day what we are really interested in is how well, from a statistical viewpoint, they were able to forecast throughput, and the best way of looking at that is how well the throughput forecast actually matched what the budget was. Of course, that's extremely important. You formulate your mine plan for the coming year, you have to forecast, you have to publish. In most cases that forecast is published, and the expectation, if you have shareholders, is that you will meet that forecast. If you don't meet that forecast, you are under, then you will not be as profitable. And as our business in mining is to make money, then that is a situation, of course, one has to avoid at all costs. So if we look here at the year 2007, if you remember, that was the very first graph I showed you where we looked at that very early model. Here we have the budget, which is 43.5 million tonnes per annum, which would have been at least supported by that model's forecast. And we can see the actual 42.4, that's not bad. They're only a variance of about 2% under that budget. So at that particular time, there would be no reason to suspect that there were any problems. And then the following year, that model would have been used to forecast next year's budget, and next year's budget was for 40 million tonnes per annum. Unfortunately, and partly because of those problems I mentioned to you, the fact that there was a shift to lower grade ore and the point load index didn't unfortunately pick it up, then what was actually achieved that year was 15% under budget, which would have had some quite significant financial consequences for the mine, which of course is what spurred them into looking at the reasons why and trying to improve that forecast model. So with the incorporation of the revised model that I described to you, we can see now the budget for the next year was 39.7 million tonnes per annum, which would have been predicted or forecast by that new model, and again almost bang on, 1.8% variance on that. And into 2010 that continued that correspondence between actual and budget. So I mean these data, the new model which used the SMC test drop weight index and the ball mill work index to help predict those ball mill limited periods, worked extremely well, and that's as far as the data in the paper went. I've not had any subsequent information back from the mine to see how well that model's going, but certainly on the basis of these last 2 years, it looks to have been doing its job extremely well. Up till now, we've been talking about what I've called power-based approaches. You might remember at the beginning of the presentation, I said there is an alternative approach, has another step, simulation-based approach. And in this case, rather than go straight to the raw data from the plant and to fit a power-based model, you can go the route of doing detailed surveys of the comminution circuit, developing a simulation model. In this case, I'm specifically looking at ag and sag mills. Once you have developed that simulation model, you then run lots and lots and lots of simulations under a range of operating conditions, and you generate large amounts of data that way. So rather than using raw plant data, you use simulated data, and from that simulated data you then develop what is effectively a power-based model using that simulated data. If you want to read up on how some mines have used the simulation approach to develop their comminution model for their geometallurgical model, there are 4 papers I've put there. They are readily available and really well worth reading them. They each take a slightly different route, but they are all based on initially doing some simulation modeling and then developing equations from the simulation model's output. The first one is to do with Collahuasi, second one Caserones, the third one a mine site, Yamana Gold's mine site in Brazil, and the fourth one the big Centinela concentrator. We're going to have a very quick look at this first paper and the approach that was developed there. My name is associated with this paper, but to be honest with you, the ideas and the way that this model was developed, I really didn't have much input to it. It was the brainchild. It was a really, really good approach of Constantino and Oscar. And you'll see Constantino and Oscar's names in a couple of these other papers as they clearly went on and developed that approach further. It was a very, very successful, but there's just a couple of things in there that are really very interesting that I want to draw your attention to. What the Collahuasi team did was to initially develop a JK SimMet simulation model of the sag mill circuit. And that's that blue box there. And they ran lots and lots and lots of simulations based on hardness data from each of their 6 UGMs. You'll see this terminology used quite extensively throughout South America, or at least in Chile, and it's based on a so-called end member description of ore bodies. So short for ore types. So 6 different ore types. They did extensive SMC testing, and so they knew in quite a lot of detail what the SMC test hardness was for each of these 6 ore types. And for each of these, they ran a whole suite of simulations where they varied the tons per hour going into the sag mill circuit. The throughput, as it varied, would change the power draw, and it changed the size distribution that came out of the sag mill circuit. So from the throughput and the power draw, they then worked out what the specific energy was for each of those tons per hour. Now, one of the things that we see in sag mills is that if you underfeed them, so they're idling for whatever reason, the specific energy typically goes up, and it can go up really quite high. And that's simply because the ball load inside the sag mill continues to draw power, even when you are treating very low tons per hour. And so you get this phenomenon that as you hold back a SAG mill, the specific energy goes up higher than you would normally expect. And so they were looking to see how that throughput versus specific energy varied and how the product size varied coming out of the end of the mill. Now, they took those product sizes and built for the ball mill circuit, not a simulation model. They simply did some power-based equations using Bond's equation. So they looked at the size distribution coming out of the SAG mill, the available power that they had here, the tons per hour that they were simulating. So from the ball mill circuit, they had for each of these simulations a kilowatt hours per ton, a feed size, and from that they could predict then what their ball mill circuit P80 would be. So to recap, for every UGM they generate a whole series of relationships between tons per hour, the specific energy of the SAG mill, and the P80 coming out of the ball mill. And when they plotted all the data up, this is what it looked like. On the y-axis then we have the SAG mill specific energy. On the x-axis we have the ball mill P80. Each of these lines here represents the response of each of these different ore types. And for the curved part of the model, they simply used this very simple power-based equation, which had the specific energy of the SAG mill as a function of the P80. Now, the important thing to note is that each of these curves terminates at a different point, and you can see where it terminates. There is then, I've drawn this horizontal dotted line, or these horizontal dotted lines. Now, the significance of this point here, for example, that transition from the curved line to the horizontal line, this is the point at which their circuit swaps from being SAG mill limited to ball mill limited. And their model recognizes that point in the sense that for P80s, and let's take this green line up here as an example, if the P80 in the ball mill circuit is less than 210 microns, it is finer, then the circuit becomes ball mill limited. And under those conditions, you have to progressively reduce the throughput so that you can achieve the desired P80. And as you progressively reduce that throughput, we see the SAG mill kilowatt hours per ton starts to ramp up. If the grind size of the ball mill circuit, and again just looking at this particular case, is greater than 210 microns, then the circuit is SAG mill limited only, not ball mill limited. And under those circumstances, basically you run it at maximum throughput for that particular ore type, and the specific energy basically is constant. So in their final model, their block model supplies to their comminution model what the UGM blend proportions were for each week, because their model worked on a weekly basis. That's that function there. They also developed a flotation model which provided for each of the UGMs what the target P80 should be for the ball mill circuit. The specific energy model that they developed, and I showed you those previous curves that it was based on, gives us then the specific energy based on the weighted proportions of UGMs and the P80 that their flotation model gave you. So once that had been executed, we take the specific energy through to the throughput equation, where we have the sag power divided by the sag specific energy gives us the tons per hour. They did further modifications to this model, and they called it the production model. It was really quite sophisticated in that they also incorporated all sorts of production issues. Planned maintenance is a good example of one. They incorporated that into their production model, so they had the most accurate means of predicting the weekly throughput depending on what the estimated operating hours would be for that particular week. So once they'd worked out or predicted what the operating hours were for that week, they'd got the tons per hour from this model. They then ended up with a forecast tons per week. So how accurate was the model? This is the graph that was published in that paper, and you can see the blue observed and the purple predicted. Really a very, very good correspondence over that period of time that it was analysed. Average weekly error of 5%, which I think is really very, very good indeed. So that's finished off an example of a simulation based approach. Whether you take the simulation based approach or whether you go directly to the plant raw data and develop something is obviously entirely up to you. One of the advantages of having a simulation based model is that it at least enables you, if the forecast starts to tell you maybe the throughput's going to go lower than we expect, the ability to then use that simulation model to run some simulations and say, well, look, we don't normally run this way. We're forecasting in a month's time for the ore type to change and for this to happen and to that to happen. Is there something that we can do in advance to change the way that we run our SAG mill or AG mill circuit so we can minimize the impact of that change? So it enables you to be perhaps a bit more proactive and to be able to plan for the future. The alternative is, of course, that one has to go back and change the mine plan because your forecast says, well, this is not a good thing to do from a mine plan viewpoint because the comminution circuit can't cope with it. So there is that added advantage to doing the simulation approach. I hope you'll agree that geometallurgical modelling from a comminution perspective is extremely powerful. I frankly don't think from a technical viewpoint it's that difficult. You have an existing circuit, you have access to a wealth of data. I should point out in that most cases you do need to spend significant amounts of time filtering typical raw plant data because there often is a lot of noise. There often are trends in the data that have absolutely nothing to do with changes in ore type, ore hardness, feed size or whatever. They are a multitude quite often of downstream influences that from hour to hour and day to day influence the throughput of your comminution circuit. So when you're building your model and when you're assessing your model, you really have to be cognizant of when those periods are, because you can't leave those in when you are developing your comminution model. By all means, develop, as Collahuasi did, a production model. That's a separate model, very powerful model that incorporates those influences as well. And you combine the two and you have something which is really very, very, very good indeed. Now, they're powerful in the sense that all these models, if they're done well, are powerful in that it is vital that your forecasts are accurate. Otherwise, as I pointed out at Batu Hijau, you can run into a situation where something unforeseen happens and you do not meet your budgets, and that can have significant and very, very serious financial consequences to your mine. Despite the importance of accurate forecasting for your comminution circuit and the potential to save millions and millions and millions of dollars, I still hear time and time again, yes, we'd love to develop a geometallurgical model, but it just costs too much money. And they're usually referring to doing test work. And I said earlier about going the cheap route, the proxy route, and it is fraught with problems. The best way to do it, simply bite the bullet and do the appropriate laboratory tests and the appropriate number of them. And yes, it costs money. However, if one looks at a typical example, and let's say it's a big low-grade deposit, and you're looking at taking one sample, one comminution test per 200,000 tons of ore in the ground, and let's just assume that the ore characterization program per sample cost us US dollars, say $2,000 per sample, then what we're looking at is spending per ton on characterization 1 US cent per ton. Having had a look at an annual report recently of a medium, fairly big copper producer, and looked at their financials and their throughputs and their profits, then just a 0.1% shortfall in annual throughput. So let's say that could have been avoided by a good geometallurgical model. Just that 1.1% shortfall in throughput would have lost them, my estimates say, 7 cents per ton of ore. So you look at the leverage, spend 1 cent and avoid a loss of 7 cents per ton for just a minor shortfall in annual throughput. With those numbers, for me, frankly, no mine can afford not to go the geometallurgical modelling route.